So the topic I'll be presenting is a JSON web signature-based adaptive authentication modality for healthcare applications. And yeah, we have been given a timeline, so we'll just rush through it. Right. So what we're presenting is an authentication modality, a new novel authentication algorithm, specifically for the healthcare sector and healthcare applications. And obviously, with healthcare, we are dealing with very confidential private data. So unauthorized access to any kind of such data is extremely, the attack surface and the outcome is not something that we would expect. But why would we need this? Because single factor authentications, though they have been prevalent, are generally not sufficient, because with evolving technology capability, computational capability, single-factor authentication schemes can also be broken, or even biometric signatures may be spoofed or can be lifted off a surface, let's say. Multi-factor authentications do mitigate this, provide better coverage. However, we do still have a problem where one or more authentication schemes may be played in sequence, and both are individually, they may still be spoofed. Now, this is what traditionally we have used to. It's a static application of MFA. Now, there are two things. One, like I said, individually it may be spoofed. Secondly is the aspect of usability. With more challenges popped to a user, it's been generally seen that users tend not to accept it or take it or move away. So this brings in the need for the concept or paradigm of adaptive authentication. Now, what is adaptive authentication? So depending on the risk, or depending on the situations, depending on the behavioral profile of a user and how much they vary from an established profile, the system starts popping challenges to the user. So which means the system continuously verifies the user or the user's behavior when interacting with the system. At the same time, keeps the challenges to a minimum. If risk is detected, how is it detected? There is a deficit in trust, and this is calculated by the variance of the user's from an established behavior. Let's say the user has been established to log in normally between 10 to 12 to a healthcare or banking application from a specific city using a specific device. Now suddenly there's a variance, the user is now in a different city, he's logging in at a different time. That is a cause of risk. So, and now when risk is noted and it exceeds a specific threshold, we can start throwing a challenge or a set of challenges that match with the risk that such an access exposes, or such an access will bring in. And what can we do about it? So the paper is not about an adaptive authentication system, but about an authentication modality that can integrate with an existing or a proposed adaptive authentication system. And we do want to introduce two known but still would like to cover JWT, JSON Web Tokens, and JSON Web Signature as well. So these are open standards defined, and the RFC is available in the IETF. And JSON Web Token, in its simplest definition, is a compact and URL-safe way of exchanging claims between two parties. And the JSON Web Signature is a way of signing data. And it has a structure, and the JWT is contained within that structure. So what is this structure we talk about? Generally has three parts. A header. It's a JSON object signing an encryption header. It denotes the metadata about the algorithm and the keys that have been used to sign this whole structure. And typically, the standard defines multiple encryption algorithms, but typically RS-256, HS-256, or EC-256 are recommended and generally used widely. This structure, if you take the example, it says that this is a JWT. That's a header section. A payload is where we have a set of claims. What are the claims? It's some information that's identifying the user or the type of interaction that we're going to have, and it is a JSON object. So there are standard defined keys, or we can have our own custom keys, key value pairs. And finally, there's a signature section wherein you sign the whole structure, with the private key. So this brings in the added advantages of authenticity, integrity, and also non-repudiation, because you have signed it, you now cannot claim that you did not. So what was the objective? Come up with an authentication algorithm that integrates with an adaptive authentication system, that it be lightweight. It use open standards so that it can integrate well with existing systems as well. Now, we also have to bring in, the need to bring in mutual authentication. So for that, established paper of secure biohash-based algorithm for healthcare devices was extended, and onto what are the changes that had to be made? One, we have reduced the computational cycles from the original algorithm and minimized the amount of confidential information that is stored either on the device or transmitted. And any computations are generally held in memory, so that if the mobile application is killed, that information is lost. So the system will have to go through it again, or it will be runtime computations. So because it integrates with an adaptive authentication system, behavioral context attributes are also captured and passed in through all the phases. And all this is structured and contained within a signed JWT, so that the authenticity or integrity as well as non-repudiation are the advantages that we gain from it. So these are some of the notations used. I'll explain it through the algorithm. So this is the attribute sets that we have defined. So a user has a mobile application. So this is specifically about mobile application usages for healthcare. So user uses an application on a device. So these are some of the set of attributes that we can gather without being too intrusive, and we can still build up a behavioral profile for the user. So this is how the flow goes. It goes in 3 phases. First time, there's a registration phase where the user information, credentials, as well as the primary set of attributes are sent to the server. How do we do that? So credentials are never sent in the plain text mode, or even if encrypted, it is still not sent. It is hashed. So this is for 2 purposes. One, there should be security while being transmitted, and also in the server, even if it is stored, there should be security when data is at rest. So we concat and compute the credentials, which now generate RSA key pair, and the claims so the claims here include the credentials, the attributes, and an expiration time, so that we know that we are assigning a time to live. If it has been, so that if it is replayed, or if it has been held and and then reaches server late, we are immediately rejecting it. And these are embedded into the JWT and signed with that private key. It is transmitted securely over a secure channel. At the server, couple of things. Yeah. So a random salt is calculated, and so this is for the purpose of generating keys and the symmetric. So all encryption done at the client and server are both symmetric, AES 256. The keys are generated both at the client and the server. It's not again transmitted. So we can compute the salt. That is to add a confusion there. We generate a unique identifier. That is to uniquely identify this user on the device. And with those values, we are the attributes have also been captured and stored. So finally, we are encrypting a message, and unique identifier in a hash form, the identifier, the combined value of ID and credentials, and the public key that is obtained from the incoming JWS are stored. And this message is sent back. So nothing is sent back to the client in plain text. Now, the client already had the ID, so it can simply compute the salt by XORing, and it is derived, and with that value, it can decrypt. So we did not have to send the key directly, only one extra value had to be sent, and that ID alone is stored securely in the client. So the login phase goes through pretty much the same set of computations, but here we also include a nonce, and again, encrypt based on the key computed locally. All this, along with the attributes, are embedded into a JWS and sent to the client server. This point, the server can immediately do 2 things. One, from the originally received signature during the registration cycle, if the key varies, because it is signed, it's a signed it is signed. So if there is a mismatch, it can be immediately rejected. If the expiration is met, the timestamp is inserted into the payload that is sent. If it has exceeded a threshold, reject. Also, the timestamp is also embedded within the encrypted the payload. So that way, even if, let's assume that an attacker has been able to tamper, even then, we still have that timestamp originally recorded with the nonce, so that it can be rejected immediately. Now, based on the value obtained, we can look up directly from the value stored during the registration cycle, decrypt, and now you get the original attributes that can be used for the adaptive authentication. So that system is not the focus of our study, but depending on the variance through machine learning or static rules, it may send a challenge back, or it may continue. If there is no variance or acceptable variance, continue with the flow. Here again, computations are local, and we compute a session key. And that session key is again not transmitted as such. It is still encrypted message, but there is enough values to compute the session key at the client. The session key is also not directly sent back. So once we have it, the client also compares. It computes the session key, holds it in memory, not stored anywhere, so that even if the application is killed, it goes through the cycle again. So here, normally authentication stops at the end of the login phase, but we're extending it with the idea of zero trust, so that because it's an adaptive authentication system, the session key is validated during a resource access phase, and all the other adaptive authentication computations are done, but session key is validated. Session key also has an expiry that is also computed only if all this matches and conditions are met. Does the system allow resource access? Sure. So this is the computational cost with, compared to the original algorithm. We have reduced the number of cycles. So we have only computed hashes and XORs here with the encrypt and decrypt cycles. Concat has not been considered, assuming it is negligible and constant. The memory usage will vary based on the number of attributes that are used. So so we have done a formal analysis using Skytha, and it has passed most of the prevalent claims. So yeah, this is the conclusion. So we have a lightweight authentication modality that can integrate with and work with the adaptive authentication system, utilizes open standards and JWS for transport, and can deter multiple attacks. So yeah.
Okay.
Thank you.
Thank you. So we may take questions after the session outside, because time is too